So welcome to this video. This is the 14th part. So this is we're we're looking at this is an exploration of Lagrange's theorem, and this is part 14 of that exploration. So last time we were able to make some interesting conclusions. For instance, we're tackling this idea. Suppose the order of G is some prime p to the power alpha, where alpha is at least 1. Does that, right? Does that necessarily imply, right? That was a question. Does that necessarily imply that there exists a subgroup H, right? That there exists a subgroup H of G such that order of H equals to the prime itself, right? And so we run into some difficulty trying to establish this, but at least we're able to think about the following notion, right? So see if you could convince yourself that if this is true, that look, okay, we may not know whether this statement is true in general. At least can we know this, that suppose order of G equals to p to the alpha, and there exists some little g in G such that there exists an element of order p to the alpha. Suppose these are true. At least from here, can we conclude? Does that imply that there exists some subgroup of G such that order of H equals to p? Right. So this is what we seem to have been arguing before. Does it make sense to you? Can you find a loophole in the argument, or do you have a better argument, etc.? So, but this begs the question, supposing this is true, supposing we've said that, okay, fine, it is actually true that if there's an element of order p to the alpha, then there's a subgroup of order p. Okay, well, what about if there is no element of order p to the alpha? What can we say about whether or not there exists a subgroup of order p, is the question, right? So let's explore this idea now. Okay, suppose order of G equals to p to the alpha, but there does not exist little g in G such that order of G equals to p to the alpha. There is no element of order p to the alpha. Well, does this imply that, so question, does this imply that there exists some H subgroup of G such that order of H equals to P, right? We're not sure about this. Is this true or not? All right, so let's see. Well, maybe, how are we going to proceed here? Okay, well, maybe the most obvious thing seems to be, I mean, at least we've tackled what it means for, well, there to be an element of order P. One method we talked about was perhaps we could find an element of the group that has order P. That would be that would help us to guarantee that there is a subgroup of order P. We thought about what it means uh, to have order P to the alpha. If a group has order P to the alpha, we had the idea that, look, whether if we pick any subgroup H of G, then perhaps the possible orders of the subgroup are going to be 1, or p squared, or all the way up till p to the alpha. Right? Those are the possible possibilities for some subgroup of G. Perhaps this is true, but did we explore what it means to not, for the group to not have an element of order p to the alpha? Right? So let's examine that. What does it really mean to say that the group has no element of order p to the alpha? All right. So yeah, what does that mean? If there is no element of order p to the alpha, how can we rephrase that? If there is no element of order p to the alpha, can we say that for all little g in G, for all elements of G, it's true that order of G is less than p to the alpha, right? If there is no element of order p to the alpha, right? Okay, So if there is no element of order p to the alpha, can we at least say that the order of g must be less than p to the alpha? Right? Did you buy this idea? Well, how do we show that something is less than that? How do we show that one natural number is less than another natural number? Right? What's the technique for that? For instance, how do we show that one natural number is less than another natural number? One integer is less than another integer. Right? So how do we establish that the order of g has to be less than p to the alpha? Well, assuming that there is no element of order p to the alpha. Well, what does it mean for order of g not to be less than p to the alpha? Does it mean that the order of g is greater than or equal to p to the alpha? But, okay, but we said that the order of g cannot be p to the alpha, right? So are we saying that order of g then, because we're saying there's no element of order p to the alpha, so are we saying strictly that order of g, for every g, order of g must be greater than p to the alpha? Okay, if order of g is greater than p to the alpha, right, how does that square with Lagrange's theorem, which tells us that the order of every element must divide the order of the group? If order of g is greater than p to the alpha, how can the order of g divide p to the alpha? Okay, how is this possible? Right. So is Lagrange's theorem telling us here that actually is Lagrange's theorem telling us here that the order of g has to be less than p to the alpha for any alpha? Okay, if the order of g has to be less than p to the any alpha, and the order of g must divide p to the alpha, what are the possible values for the order of g? Right? Are we saying that the order of g has to either be 1 or p or p squared or all the way up till p to the alpha minus 1 in this case, right? Because aren't we saying that order of g is less than p to the alpha? So if these are the only possibilities for order of g, well, let's ask the question, is there anything we can eliminate off the bat? So suppose we pick g not equal to the identity, right? Or let's ask the question this way, how many elements are there in a group such that their order equals to 1? Or stated differently, is there any non-identity element in a group, let's say g not equal to the identity, such that its order equals to 1? Is that possible? What would it mean for the order of an element to be 1? Wouldn't it mean that g to the 1 equals to 1? But if g to the 1 equals to 1, aren't we saying that g equals to 1? But didn't we assume that g does not equal to 1? Alright? So are we saying that at least we know that if we pick, if g is not the identity, and we're saying that the order of g has to be 1 or p squared up to p to the alpha minus 1, if g is not equal to the identity, can we at least cross out the case when the order of g equals to 1? Okay, so what are we saying now? Are we saying that if we pick a non-identity element in our group here, right? Are we saying that if we pick a non-identity element in our group, at least what we know is that the order of g has to either be p or p squared or blah blah blah, okay, up to p to the alpha minus 1, okay? Well, okay, can we determine which one the order of g has to be, right? Can we determine if order of g has to be p or p squared or p cubed, right? So perhaps it's not so clear how to do that, but what we do know at least is that, well, order of g has to be one of these, right? So how is this information helpful to us? Right, so let's see. Let's suppose that order of g equals to p to the I, where I is one of these numbers, is alpha minus 1 and 1, right? The power is alpha minus 1 and 1, right? So if we can assume this, now let's ask the question, well, if order of g equals to p to the I, where I is between 1 and alpha minus 1, well, can we say the following, that what about the cyclic subgroup generated by g, right? So can we say this, that let's call it h if we like, let's call it h, sure, or m, or we've been using h too much, let's call it m. Consider the set m equals to g to the 0 g to the 1, g to the 2, all the way up till g to the p to the I minus 1, right? Since order is p to the I, right? Can we at least say that this set M is a group, right? Is it a cyclic group? And if it's a cyclic group, is it a subgroup of the group G? All right. In fact, it has to be a proper subgroup, right? So if M is a proper subgroup of the group G, right, then all right, at least we've reduced the power. Now, haven't we found a subgroup of G whose order is p to the I, where I is less than alpha minus 1. Sorry, less than alpha, right? So we've reduced the power, right? Now, suppose that let's say for this M that we picked here, we actually found an element of M. Suppose there exists some little m in M such that order of little m equals to p to the I, right? Okay, suppose we did this by our argument before, right? Remember we said that, look, if we have a group whose order is p to the alpha, and there exists, right, we're saying this, and there exists some g in G such that order of G equals to p to the alpha, so long as there's an element of order p to the alpha, then we are guaranteed a subgroup of order p for the group, right? So suppose that in this subgroup of G that we formed, we actually found an element of order p to the I, right? Isn't a subgroup, right? The question is, right, before we found that, look, if we have a group of order p to the alpha, and we have an element of order p to the alpha, this guarantees us some subgroup of order p in the group. Well, we've gotten the group G, and we've taken a subgroup of it, a subgroup of order p to the I, right, where p to the I is strictly less than p to the alpha. And so we said, okay, well, what we said was, look, M is definitely a subgroup of G, but in particular, if M is a subgroup, isn't M a group as well? Okay, if M is a group and the order of M is p to the I, okay, so can we at least conclude the following, that there is some little m in M, right? Oh, no, I mean, we can't agree, but suppose that there is actually some little m element of our our group M, of our subgroup M, whose order equals to the order of the group, equals to p to the I. Can we also conclude by our previous theorem here that indeed there must exist, so implies that there exists a subgroup, let's say L, subgroup of M, such that order of L, right, such that order of L equals to P, right, just by the same idea before. Because we said if there's something of order P to the alpha, and there's an element of order P to the alpha, then we have a subgroup H of G, such that order of H equals to P, right? Analogous here. A subgroup is still a group. So if we found an element of order M, right, if we found an element in this subgroup M of G, if we found an element M of order P to the I, right, are we able to conclude that there is a subgroup of M such that its order equals to P? If we're able to do that, isn't it true that if something is a subgroup of M and M is a subgroup of G, then L is a subgroup of G, right? So haven't we found a subgroup G of order P, right? Okay, so maybe the question now becomes, well, okay, this is all well and good, but what if there is no element in our subgroup M that has order P to the I? Okay, well, can't we just argue by the same way and find if there is no, suppose, right, suppose there is, for the M subgroup of G, where order of M equals to P to the I, and P to the I has been chosen to be particularly less than P to the alpha, right? Suppose that for this group here, of order M equals to P to the I, no element, right, there doesn't exist G, or let's call it M in M, such that order of M equals to P to the I. Okay, suppose this isn't true, right? There doesn't exist that. Well, can't we use the argument we used before to say that then this implies that, right, if we pick any non-identity element of the subgroup M, if we pick any non-identity, let's say, I don't know, let's call it M2, not equal to the identity and M2 element of M, can't we say that the order of M2 has to be strictly less than p to the I, right? And so if let's say order of M2 actually turned out to be p to the j, and p to the j being strictly less than p to the I, well, can't we at least conclude from here that, look, well, now we found a smaller subgroup. We found maybe some other subgroup. Let's call it S or whatever. Wouldn't we have found another subgroup S of M where order of S is strictly less than order of M, right? And then we kind of continue with the process here. Either order of S, either in S there exists some S in S such that order of S equals to p to the j, or there doesn't. Here p to the j is being taken to be less than p to the I. If there is, then we're done. We found a subgroup of order p. But suppose there isn't one. Can we at least conclude from here that there must exist some subgroup k of S such that order of k equals to, let's say, p to the t, which is less than p to the j, for instance. And if there's an element k in k such that it has order of little k equals to p to the t, then we have a subgroup order p. Otherwise we don't, in which case we reduce. I don't know if, is this making any sense to you? Right, is the question. So we seem to be coming up with this idea. We get a group, we start with a group G, alright? Well, the group G has order p to the alpha, say, okay? Now, either it has an element, right? Either G has an element of order p to the alpha or it doesn't. If G has an element of order p to the alpha, aren't we done, right? Doesn't that mean that there's a subgroup of order p? Okay. So let's see if this, I don't know if this argument, you buy this argument. So like, so how to write it exactly? Okay, we start with a group G of order p to the alpha. Order of G equals to p to the alpha, okay? Now either G has an element of order p to alpha, or it does not, right? Let's write it like this: no element of order p to the alpha. If it has an element of order p to the alpha, well, then we're done, right? Don't we have a subgroup of order p? Okay. Isn't that what we proved last time? Okay. Suppose it has no element of order p to the alpha. All right. Then can we at least find a subgroup h of g? Right now, subgroup h of g such that order of h equals to p to the j, right? Where p to the j is strictly less than p to the alpha, right? Right. So if we can find such a subgroup, can we say the following? Either there is some little h in h such that there is some element of h whose order equals to p to the j, or there isn't. There is no h whose order equals to p to the j. If there is an element whose order equals to p to the j, can't we say that h has a subgroup of order p? And if h has a subgroup of order p, right? So here, can't we say that we're done at this point? Okay. Well, if we're done there, well, what if it actually turns out that there is no element of order p to the j, right? There's no element of order p to the j. Well, does that tell us that there must exist some subgroup of h, let's call it L, such that order of L equals to p to the t, where p to the t is less than p to the j, right? If that is true, well, this L either has an element of order p to the t or it doesn't. If there exists some L of order such that, if there exists some little L in L whose order equals to p to the t, well, aren't we done then? Right? Aren't we done? Alright? But suppose there doesn't exist such an element, right? Aren't we just going to reduce the powers even more? Right? So, are we talking about a reduction of powers here? And if we keep reducing the powers, does this process stop? Right? If we start from some p to the alpha, right, where, well, p is a prime and alpha is some number, and we keep reducing the powers to potentially p to the alpha minus 1, we don't know what it will be, potentially p to the alpha minus I, does this process stop? Right? What happens when I goes to alpha? Doesn't that give us p to the 0? Right? So is this convincing, and is this a convincing argument that, look, if we can always, if the only two options we have are that, look, either there is an element of the order of the group or there isn't one. And if there's an element of the order of the group, well, we're guaranteed that we have a subgroup of order P. If there isn't one, then we at least guaranteed a subgroup of order whose order is less than p to the alpha, right? So it's p to some power, but less than p to the alpha. All right. All right. We just run out of time, so let's just clarify this. Is this a convincing idea to you? And in particular, is there anything that can go wrong? So okay. Or what could possibly go wrong? Could we ever reduce powers and go to like some p raised to some negative number? I don't know, -2 or something. Is that possible? Right? Question. And maybe another question to think about is, okay, if we keep reducing the powers, is there any way we could reduce them and end up not getting p? Right? So, I mean, if we reduce the powers and let's say go to p squared or p to the third, right? Well, either the subgroup of order p to the third has an element of order p to the third or it doesn't. Suppose it had an element of order p to the third, right? Wouldn't that mean that we have an element, we have a subgroup of order p? Okay. Suppose the element of order p to the third has no subgroup of order, it has no element of order p to the third. Wouldn't that mean that we need to reduce the power? Okay, well, what are we going to reduce the power of p to the third to? Well, I mean, if we reduce it to p, then haven't we just found a subgroup of order p? Suppose we reduce it to p squared, right? Aren't we done then? Because, okay, look, either there's an element of order p squared or there isn't. If there's an element of order p squared, we have an element of order p, right? Otherwise, if we don't, then we said that the only possible available options for subgroups, if there's no element of order p to the alpha, are always going to be p to the 0, sorry, p to the 0 is actually, we said that was the identity. And in particular, we're picking what's it called? We're picking elements whose order was not equal to the identity. So wouldn't that, or non-identity element. So if we're saying that, let's put it this way, just to make it really clear. If we're saying that, look, anytime we do this reduction, we always have, the possible orders are always p to the 1, or p to the 2, or p to the 3, or p to the 4, or blah 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 up to p to the alpha, let's say alpha minus 1, right? Okay. And every time we do a reduction, we're cutting down the powers. Let's say we cut down till p to the 4, okay? And p to the 4 either works for us, that is, either p to the 4 gives us an element, either the subgroup of order p to the 4 gives us an element of order p, or it doesn't. If it doesn't, then we're left with the powers less than that. Well, maybe we get p to the 3. Well, if p to the 3, if the subgroup of order p to the 3 gives us an element of order p, we're done. Suppose it doesn't. Okay, well, we're going to reduce powers then. So now we're left with 2. Suppose it's p to the 2. Well, if it's p to the 2, then either the subgroup of order p to the 2 gives us an element of order p, or it doesn't. Well, suppose it doesn't. Well, what are we left with? Is it convincing to you that it doesn't matter how you look at it? If we have a group, if we have a group of order p to the alpha, then whether there's an element of order p to the alpha or not, by performing this process of reduction, eventually we end up with the idea that there must exist a subgroup h of g such that order of h equals to p, order of h equals to p, right? Do you buy this idea? Is this a convincing argument for you? Alright, well, we actually ran out of time already. So thank you very much for watching this video, and have a relentless week. Bye.